So let's look at another example. Two fair six-sided dice are rolled and the variable x represents the number of sixes obtained. Alrighty, well, first of all, let's just think about the possible outcomes. Well, if you get no sixes, 1 6, or 2 6s, right? Those are the only possible outcomes of this particular one, right? So this is x, and p of x. Alrighty, so let's have a think about all of the different outcomes. So if I think about trying to work out this is a probability distribution table, I have to think about all of the different ways I could get it. So let's do the easiest one. How many different ways can I get 2 6s? Well, there's only one way. It means on the first dice roll is a 6, and on the second dice roll is a 6. And that means that there's only 1 out of 36 different outcomes that could be achieved that way. Now, let's think about how many different ways I could get a 1. Well, either I get a 6 on the first roll and then a 1 to 5 on the second roll, or I do the opposite, right? I get a 1 to 5 on the first roll, and then in the second roll I get a 6. So this represents 5 different outcomes, this represents 5 different outcomes, so it's 10 different outcomes out of 36. And so then that just leaves us with the cases in which I get a 1 and then a 1 to 5, or a 2 and then a 2 to 5, or so on and so forth. Or I could just think of it a 1 to 5 and then a 1 to 5. So it's 5 outcomes here, 5 outcomes here, 5 times 5 is 25 outcomes out of 36. You might be wondering, where am I getting 36 from? Well, it's just because there are 36 different outcomes when you roll 2 to 6, six-sided dice, right? Because there are 6 outcomes in the first one, 6 outcomes in the second one. So 6 times 6 is 36 total outcomes possible, because order does matter in this sort of game. Alrighty, so that's just my probability distribution table. Where do I go from here? Well, I need to calculate expected number of sixes obtained. So we're looking for EX. Alrighty, now we've been working with uniform distribution tables, but the fact that this one's not a uniform distribution table should remind us we need to remember how to do that as well. So we're going to get 0 times 25 on 36 plus 1 times 10 on 36 plus 2 times 1 on 36, 0 plus 10 on 36 plus 2 on 36, 12 on 36, which is just a third. So the expected value is a third. And what about the variance? Well, once again, for variance, let's square x. So we're going to get 0, 1, 4. And we need to work out E of x squared. 0 times 25 on 36 plus 1 times 10 on 36 plus 4 times 1 on 36. It's a very similar calculation to the previous one. 10 on 36 plus 4 on 36, 14 on 36, 7 on 18. Alrighty, so now to work out the variance of x, let's use our normal variance formula. E of x squared minus E of x squared. And we get 7 18s minus a third squared. 1 on 9. 1 on 9 is better written as 2 on 18. And we get 5 18ths as the variant. Alrighty, so there is another example doing this. And just for this beginning part here, just before I finish the video, you could have obviously done this with a tree diagram, right? You could have done this with a tree. Just be careful with it. Works great for some examples. Some examples it might take too long to work out. So obviously you could have just done this with a tree diagram. I chose not to do it that way. There are many ways of working out probabilities. Anyway, I'll see you in the next one. Bye-bye.